application, soon to be the GOES application, because GOES 17 will be operational before we know it. We're very happy today to have Pete Wolf, who is the Sioux in Jacksonville, talking about how they're using GOES 16 data down there for Lightning decision support. Go to the next slide. This is part of a series of presentations given by your peers, and there are recordings of those online at the links that are at the link that is indicated. If you want to give a talk, send an email to me. I'm Scott Lindstrom, or to Dan Bikus. We'll be happy to guide you through how to do this. I hope it's not that painless. Pete can say yes or no. I hope he'll say it's not painless. Go to the next slide before we can say anything. We'll have about 20 minutes for the speaker. Send questions to go to chat if you want to, or there's a Q&A afterwards. Following the Q&A, there'll be some open discussion on GOES 16 and 17 in general. We should be done by the 18:30 UTC. Don't press hold, and put on your mute. Take it away, Pete.
Okay, thank you very much. So the title of the presentation was about making the impossible possible, and I'll get to what that means here shortly. I want to start with the question, why is Lightning decision support a big deal, which is kind of what this talk is about, and as far as we talk about how we utilize satellite for Lightning. And really, it's changing our priorities. The old Weather Service priority was that warnings always come first, but maybe this is changing as we start thinking more about impact. What I'm showing here is an example I've given to our staff here, where you have two thunderstorms on a July 4th holiday weekend. The Storm 1 is a severe hail-producing storm over the swamp, and we have lots of swamp here in northern Florida. No people live there, but it's likely pelting alligators with golf ball-sized hail. And then you have Storm number 2, which is a non-severe storm, but one with considerable lightning that's approaching a heavily populated beach. Our old Weather Service priority approach was that warnings come first. And so we would focus on Storm number 1, even though it's in the middle of nowhere. But the approach of our evolution towards decision support services and towards impact as opposed to just weather may lead to a change in that priority where, in this case, number 2, affecting a lot of people and structures, might be of the higher priority. This talk is really going to focus a lot on lightning and what we're going to be doing on lightning and how we're going to incorporate satellite as well as radar in this focus on lightning DSS. There's been a lot of studies in the past on utilizing radar reflectivity structure and using that to anticipate cloud-to-ground lightning initiation. Mine was one of many that focused on the minus 10 Celsius isotherm and looking for when the 40 dBz core extended to and above that level. Now, one difference that I made versus a lot of the other studies, most studies looked at the environmental minus 10 Celsius isotherm, which is the lower level on the sounding that's shown. However, it can't be the same in the updraft, otherwise there would be no positive buoyancy. It has to be warmer in the updraft core, and so I focused on more of a theoretical updraft minus 10 Celsius level using a theoretical updraft parcel. And it can be in a moderately unstable air mass thousands of feet higher. And that makes a difference with regard to how well, for example, the MRMS isothermal reflectivity works or doesn't. So what I found in my study, mine was a large one. I did 1,100 cells, and it was focused on the southeastern U.S., so results may differ in other types of environments that may exist, more extreme instability in the plains, for example. But what I found was that as the 40 dBz core, at the height of that approached minus 10 Celsius, we started seeing lightning cases versus none at all. And as we got above the minus 10 Celsius level in the updraft core, the probability rose above 50%. And it continued to rise as the height increased. In fact, as it got about 15,000 feet above the minus 10 Celsius level, we started seeing the potential for numerous strikes increase about 50%. So we saw actually a relationship between how the depth of that core above minus 10 Celsius level and the amount of lightning that actually occurred. So radar, along with dual pol, which also now allows us to actually visualize global, because we're looking at particle shape, it can allow us 5 to 10 minutes of lead time on lightning initiation. Obviously longer for fast-moving and longer-lived stuff because you can see it coming way in advance, so you can get more lead time that way. But for storms in the warm season in our area, for example, where it just develops on top of you, probably 5 to 10 minutes is a good average. It can also allow us to estimate approximate cessation time, but there is uncertainty, and I'll get to a little bit of that later. We also now have some really interesting and useful GO16 tools with regard to understanding particle phase and how that may support lightning development. One is the day phase distinction RGB, which is shown in the upper right. Of course, it's only available during the daytime, but that's when most of our thunderstorms occur anyway. And it is used to indicate when cloud-to-ground lightning is possible. When we start seeing shades go from blue to green and then to yellow, we're introducing ice, but it's not a guarantee that lightning is going to occur. It could be graupel that we're starting to see. It could be ice crystals in an anvil that we're starting to see. So there are occasional false alarms with this product, so that's why I'm talking about it as a tool for indicating possible lightning development. And that provides us, up to 10 minutes for in-cloud, maybe up to 20 minutes for cloud-to-ground strikes as far as lead time is concerned. It utilizes band 5 for discriminating between water and ice. And then we have the GLM, which detects total lightning, and it's a useful tool for indicating where cloud-to-ground strikes are likely or imminent. It's total lightning, so it's focused on both in-cloud and cloud-to-ground. In-cloud tends to occur first, and therefore when it's detected, obviously providing 0 lead time, but it could provide up to 10 minutes lead time on cloud-to-ground initiation. It, however, overestimates the area of lightning, potential lightning occurrence, and I'll demonstrate that here shortly. If we want to get longer lead time than that for decision support, well, then we have to turn to convective allowing high-resolution models, such as the HRRR. And the HRRR in the cool season for organized convection tends to be quite good, although its timing of initial development, arrival, and departure can be questionable at times. It tends to be very good for long-lived convection. This time of the year for short-lived pulse convection, terrible, absolutely terrible, not useful in this purpose. We're left to focus on radar and satellite. Our focus is on creating a decision support program for our core partners, and success of that means we need to go beyond simply telling them when lightning has been detected by the NLDN network. We need to be able to anticipate initiation as well as to anticipate cessation. To do that, the success really depends heavily on A, forecaster knowledge of storm environment, B, obviously the ability to access real-time satellite and radar data. Also, we need to have knowledge of the issues and biases associated with these data sets, and overall knowledge of the process of how lightning is produced in thunderstorms, the important role of graupel, for example. We have a lot of experience as far as radar is concerned with the issues associated with it, increasing beam height and width with range from the radar, the amount of interpolation and the impact of interpolation between elevation slices at longer ranges, whether a radar is running warm or cool, and so forth. We have the dual pole. This is an example that shows in the magenta color the graupel, but there might be times when that classification is overwhelmed by another classification. And then there's MRMS, which again uses the environmental minus 10 Celsius level. Unfortunately, at that level, when you have at least moderate instability, it's related to more of a -4, -5 Celsius temperature within the updraft core, and that may not be low enough to support introduction of ice, and you may just have supercooled water and no lightning. So more in the way of false alarms, just using this MRMS isothermal level based on the environmental levels. So we have a lot of experience with that. As far as satellite is concerned, well, prior GO satellites really didn't provide a lot of value for anticipating lightning. I mean, you could look at visible imagery and see growing cores, but you couldn't tell if a core had graupel in it or not, so forth. So there was nothing to discriminate between the different reflectance properties of ice. But the new GO satellite is a potential game changer, although we are still in learning mode on this. The RGP, the day phase distinction RGB, gives us indications of when we're introducing ice into the core, or if it's ice crystals in an anvil. So there are risks of false alarms with this. Not every storm that shows the colors towards green and yellow end up producing lightning. But it is a pretty good tool, along with knowledge of environments, to anticipate when there's potential for lightning to initiate. And it really works well when you combine it with radar reflectivity structure as well. If you have the colors changing and you actually see 40 dBz core also approaching -10, likely you're seeing graupel in both sections, and you can go from there. GLM also very useful. It is like a camera. It detects light that's reflected to the satellite from lightning. So it helps us to see, particularly in-cloud strikes, which tend to occur usually before cloud-to-ground strikes. However, the way it's generated can yield potential for misinterpretation. It detects reflected light, which usually comes from the lightning strike, but it can also come from distant clouds from which that light bounces off the cloud and back toward the satellite if you're dealing with a really intense cloud-to-ground strike. And I'll show some pretty interesting examples of that here. So here's one in the eastern Florida Panhandle, and you actually can see a little sense of the parallax that's here with lightning. The dashes are the cloud-to-ground strikes. The gray areas are, I think, EM, TLM, total lightning. And so you're seeing it a little south and east of the core, I think, through the parallax. But anyway, the lightning is mainly east and over the eastern and southern part of this storm. You'll notice some low clouds off to the south and west and off to the north and east. And so when I show you now the footprint for the GLM, it picks up, obviously, the lightning strike there, but notice the extension of particularly the dark blue shade, all the way multiple counties to the southwest, off to the northeast, and so forth. And I think what we're seeing, I don't think there's lightning all over this area where these low clouds are. I think what we're seeing is the light from very intense cloud-to-ground strikes reflecting off of these low clouds that the satellite is picking up just enough of to indicate in this footprint. And that kind of bias is important to understand to correctly indicate where and when the threat of lightning exists. Here's another example, and you see a lot of cloud-to-ground strikes, in this case, particularly on the eastern and northeastern part of this cluster of storms. And you see a lot of low clouds extending northeast of that. So you can probably guess it before I even show you where the footprint's going to extend on the GLM. And there you see multiple counties well away from the storm where there's no clouds whatsoever. It's not likely numerous, bolts from the blue. It's most likely light that's reflected by these very intense cloud-to-ground strikes off of these low clouds. You'll notice off to the southwest we have low clouds there, but we're not seeing any footprints in that area, probably because the storm itself is blocking the light from where the lightning appears to be occurring. Here's another interesting example. Note this one in the middle here. I'm trying to point out with the cursor. It's over the downtown Jacksonville area. And we have a cloud-to-ground strike on the eastern side of the core. You'll notice there's a few low clouds just east of the center, but further than that, there's nothing, dead clear. And if you look at the GLM, you see the footprint right where those low clouds are, but it does not extend further east where there are no clouds. You also see the extension of the footprint with the storm to the north, again to the east, nothing to the west. There's lots of low clouds to the west, but there's no footprint there because all the lightning in this particular minute is on the eastern side of the storm, and the same thing with the storm to the south. It's pretty interesting to watch over the course of the time and see where the clouded ground strike is and then see where the footprint actually develops during that same minute. So that's the title of this presentation, and that's making the impossible in DSS possible. The impossible is that in lightning, despite the fact we're here in Florida, it's the number one weather-related source of fatalities and injuries, we're not really staffed to provide lightning alerts and warnings for the general public for every potential location, because every single thunderstorm obviously produces lightning. The workload would just simply be too great, be too easy to miss storms. But, and now I say that noting that 10 years from now, that could very well change. As we incorporate these new data sets, I can certainly envision, as we have a prob severe and a prob tor, I can envision a prob lightning that incorporates what I've been talking about in a probabilistic way and allows us to provide alerts to the public. That could come in the future. For now, the possible is based on the Weather Service evolution that focuses on threat messaging through and for our core partners. So for our office, we're focused on looking at the emergency managers who support, the Jaguars game at the outdoor stadium, lifeguards that support the public beaches, airports, military bases, and so forth. These are the cool partners we're really focusing on with regard to providing lightning support for outdoor events. And if you have a chance to think about this probabilistically, based on what we are now provided with satellite and radar, most of the time we're going to be all clear in the green, if you will. But maybe the day the phase distinction RGB starts to show growth and introduction of ice, maybe we see that with radar starting to grow core close to minus 10 Celsius level, and we can say that lightning's possible at that point over the next 20 or 30 minute period. So that would be like kind of a yellow phase. And then when we start seeing the radar show the core getting above minus 10 Celsius, if we start seeing in-cloud lightning starting to be detected on the GLM, we can go to red being imminent or likely. Likewise, for cessation, we can go the reverse way. And there are challenges with regard to cessation. The core itself, even though the core falls apart, lightning can continue if you have charged particles that have affected along an updraft or through a stratiform region behind a storm. And cloud-to-ground strikes can continue for some time. And this is kind of important training that the forecaster has to have to best understand when to indicate the cessation of the lightning threat. I'm going to show you some quick examples here. I want to tell you of one example first that we went through. Let me see here. So we had a case a few weeks ago with a Leonard Skinner concert in downtown Jacksonville at the outdoor stadium, and we were supporting the emergency manager there. On 2 occasions, we had thunderstorms develop just upstream of the stadium and then produce cloud ground strikes around the stadium itself. In both cases, we provided about a 10-minute lead time using the techniques and information that I just showed you. In both cases, they end up issuing a code blue, which is to clear off the stadium and to delay the show. So it was a really good success, an illustration of how well this can work, I believe. I want to show you a quick example here, and to do that, I need to get out of this PowerPoint here, and I'm going to call up, give me 1 moment to call up the case here. What I'm going to show you is an animated GIF, and hopefully you now can see it. And we want to focus on Jacksonville, which is where the cursor is, and Jack's Beach, which is on the coast. And I'm showing you the RGB with the GLM overlaid on it. And think about, for those particular locations in downtown, when we might go from green to yellow and alert partners, when we might go then to red to indicate, lightning is imminent. And you can see really this convective system sending an outflow boundary north. At this point, we'd probably go yellow, if not red, as it starts to initiate storms northward as it interacts with the sea breeze. I'll let this run one more time, and again, you can go through it. And again, think about, from a probabilistic sense, at what point we can alert core partners that there's potential for lightning coming up maybe in the next 30-minute period, and then when it's imminent or likely. So we'll go through this one more time here. So again, Jacksonville downtown, the stadium is right here. Jack's Beach is on the coast. We start seeing this green shade on the RGB, but the radar does not show much of a core aloft. So in fact, it falls apart. So in that case, we probably wouldn't go with the yellow. Later, we'll see its outflow boundary coming from the south. We'll start seeing new developments occurring. I probably would go yellow just ahead of time, seeing how this is all evolving, and then a red as it approaches the stadium for action to be taken. You see in both cases there, it's affecting the stadium area and the beach area as well. So this is kind of a concluding slide. Basically, with new tools and technologies come new opportunities, and this is a really good example of one, dealing with a hazard that we really have not dealt with very well or very consistently. To do so, to be able to go beyond alerting people for detected cloud to ground, to actually anticipate initiation and cessation. Those are the 2 key points we're worried about, not in between, because obviously you have thunder and that alerts you for you. But we're focusing on initiation and cessation. It requires the meteorologist to understand storm environment, the issues with the new technology that we have, and the knowledge of the process itself that leads to initiation as well as cessation, and some of the caveats that are associated with it. And that's the end of what I have. I think it's went exactly 20 minutes or so, and I will be happy to answer any questions that you might have.
Great, thanks, Pete. If anyone has questions, unmute and ask.
This is Bernie from Fort Collins. I have a question. So in your office, I'm assuming you're bringing your forecasters up to speed. So can you give us an estimate of the spin-up time in terms of understanding what you've presented to us?
So our office is looking to do an experiment in early 2019 with a subset of core partners, a couple of downtowns, a couple of beach partners, a couple of airport partners, to do a test to see, first of all, if this is doable, if the information we provide them is what they want, to try and get feedback. And so our plan is over the wintertime to provide staff training to go through case examples. I've gone through 6 good examples of really active events that have worked amazingly well that we'll run through the staff on. And the really key to this is trying to keep workload as low as possible. And that's also our focus. How do we do this without overwhelming the staff, given all the other duties that are required, such as issuing severe storm warnings? This is important, and we need to have someone who's focused on it. So we'll be dealing with that early in 2019 and doing about a 6-month experiment, see how that works, get feedback. If we're successful, then we'll look to expand upon that and probably bring some other offices in as well. So that's the plan right now. It's going to be on one-on-one type training using actual hands-on case exercises, and then discussion about why they see what they see. That's the approach we're going to take.
Thanks. We'll be interested in hearing about it.
Excellent. Any other questions?
Yeah, hey Pete, this is Brian Mata. How are you?
Okay.
All right. So the graphics you showed were not the gridded data, the flash extent density.
Right. That was off of the zero page, I believe. That might have been optical energy.
Right. So, but what you have in Ellipse is the flash extent density, right?
Right.
So is that the gridded data set that you were using?
I expect we're going to mainly focus on flash extent density.
Okay.
Yeah.
And yeah, I was wondering if you were getting the other two grids as well, the total optical energy and the average flash area.
I know initially we wanted that. That may have recently changed. I have not recently looked to see if we're getting that now. I assume we should be, but I haven't actually looked. If we are, then we'll incorporate that in the training as well.
Okay, yeah, it probably would be a good idea since they're coming, soon, and I know you're working with Chad on this, so he could help you out with that as well.
It'll be interesting to see if there's a relationship between optical energy and the extent that the footprint on the extent density goes. I mean, if there's a relationship between the two where we have larger values of one lead to a greater overextension of that footprint on the other.
Right, there are similarities, but between the grids, but there are also some differences too.
Okay.
Okay, thanks.
Yeah.
Hey Pete, Mike Stavish, how are you?
Doing well, Mike.
Hey, so you mentioned briefly parallax. This was discussed recently among the staff. Are you coming up with any ways operationally to account for parallax in near real time?
Honestly, we are not. And obviously, for our location, it's not going to be quite as bad as, say, places in the northern U.S., I would assume. But
yeah, right.
As long as our staff is aware of that, I'm okay.
Okay, yeah, that's just something that we've talked about. That's, it's sort of an operational issue that certainly once you get further from the sub point of the satellite, it's kind of a bigger issue, and we're trying to brainstorm ways on how to sort of account for that in real time, and just obviously the synchronicity between the ground strikes and your GLM pixels there didn't look, it looked pretty good. So I get it that you guys probably aren't challenged with it too much down there, but I was just curious.
Yeah, that's a good point. It's like everything. It's like everything else, Mike. The radar is the same thing. We have issues a long way from the radar of the amount of interpolation between slices and how that affects the data that we get. So as long that's key to, I think, the training is going to be understanding the issues and biases that exist and being able to account for them. That's true for all technology.
Yep. All right. Thank you.
Yep. Any other questions?
If there aren't any questions on Pete's talk, are there any general GO16 or GO17 questions? You might have noted that GO17 is in mode 6 testing right now. So if you're looking at that, you're getting 10-minute full disk imagery now. I've also heard that on October 1st, they will be doing some simultaneous mode 4 testing for GO16 and for GO17, unless it's a critical weather day. So that's the maximum data flow for GOES-R. So it'll be interesting stress test. are no more questions, I will thank Pete, and we hope to see you, generally the audience, at some point in the near future for another FDTD Goes Applications webinar. Thanks.